Now we're going to switch a little bit, and we have a panel on advanced manufacturing. Tim Franta, who is our advanced manufacturing project leader, will be moderating that. So if our advanced manufacturing panelists can bring forward. And one other thing which we want to highlight for those of you who haven't been able to see the electric bus and the Shallow Creek CNG long haul truck, each of those are going to have to leave about lunch for other obligations. I think the bus is going to Disney. So if you haven't had a chance to see them and you want to, please make sure that you get out there and check those out. But advanced manufacturing will start in about 5 minutes. Thank you. Oh, start now. Okay.
Start now. Because I do not want to be between you and lunch, which I am. So we're going to be the most efficient panel. Yes. I am not going to speak, except I'm going to say two things. One is about the title of the panel, which, there it is, Reality and Opportunity versus Fantasy and Aspiration. And this was deliberately chosen because many things about advanced manufacturing, 3D printing, it's going to change the world. And our partners at NASA, they're going to be printing food very shortly. And recently in the news, you've seen about guns you cannot detect in X-ray machines. And of course, obviously in the article is about it's the third industrial revolution. So we wanted to address some of that because this stuff is very hard, and to get that point takes a lot. These are four of the most pragmatic guys. I had about 100 people to choose from, but these are very pragmatic people on how to get things done. The other thing I want to say is, why is the Energy Consortium concerned with advanced manufacturing? And let me share two things about that. And these are two key reasons why we are concerned. One, as I said earlier, 73% of energy is consumed in buildings. Well, out of that, a good portion of that is manufacturing buildings, but about 1/3 of all energy in the United States is used for manufacturing. So any improvement to those processes reduces the cost of manufacturing. Second, and this is probably where most of this panel comes in, most new clean technologies, most, not all, require either advanced processes, advanced materials, some sort of new manufacturing technique in order to be done. I mean, we're working things from coatings to turbine blades. We have someone with a unique materials who'll be discussing it. So we have a really interesting panel, and we're just going to get right to it. And Mr. Newton, and I'm going to let the panel introduce themselves so as not to take up time.
Okay, my name is Mike Newton. I'm with Newton Cyberfacturing. It's a spin-out company from Cyperio, which I'm the strategic technology director. And what we are, so we work with a number of universities, and again, spin out of Cyperio. We also have Nscript, which is a capital equipment manufacturer for doing direct printing technologies. Kind of start with cyberfacturing. What is that? We really do manufacturing, but in the direction of the way technologies are going, we believe that 3D is going to be a new way of building things. And we've moved into the cyberspace, so there's a lot of digital media that gets tied into that. And so what we wanted to talk about is cyberfacturing, which is something that gets people's interest because they don't know what it is, and it's something to talk about. And we believe it's the next generation way of making things. If you're familiar with your 2D printer, you basically print pages. The printer doesn't care what page 1 looks like versus page 2. All it cares about is the digital data that it takes, and it takes the inks and mixes the inks and gives you an image. If you liken that, and if you basically think about it in the 3D world, what we're moving towards is basically widgets per minute. And where we're focused on is really integrating electronics. My background is in electronic packaging, and how do we bring in the electronic functionality into what traditionally has been additive manufacturing, 3D printing of mechanical structures, and how do we add other functionality like sensors and electronic capability. As alluded to earlier by Tim, there's a lot of media press on 3D and digital manufacturing. You know, whether it's hype, you know, we'll wait and see. But I believe that this is going to be the next generation way of manufacturing. So what is additive manufacturing? It's 3D printing is basically adding materials and basically spatially controlling materials in the 3D world. It's been around for a long time for prototyping, doing mechanical mock-ups, and so it's been around for over 20 years. What's been changing though is the resolution and the material technologies that are being integrated. And so as we move into custom manufacturing, which is at least the first level niche, whether it's in the DoD realm or other custom manufacturing where you're starting to add small lot fabrication, you know, that's kind of where we're going. Ultimately, high volume manufacturing is a little way out because there are challenges in 3D printing. And if anybody's familiar with 3D printing, it's a fairly slow process. And so we're looking at ways to do that. Additive manufacturing, whether it's, and again, you look at different types of materials. A lot of people are doing work in metals. There's different ways of making a part. Where 3D gives you is the ability to take advantage of spatial control of the material so you can optimize strength versus weight based on the ability to 3D print. And that ability is really, again, living in the digital world, being able to do a 3D model and be able to control whether you're making metal sponges and you literally, the shape and the voids are designed in. So you can get structural strength and you can get lightweight. When you work in the DoD world, as we are, size, weight, and power are a big deal. And so these are the types of structures that you might look at, and why are they important? Well, there's some very creative things that you can take advantage of that, whether it's in fuel cell technology or other types of thermal management technologies. Where are we in the world? We're still at the front end. We are approaching. We're moving towards the knee. Probably the low-hanging fruit is definitely structural. Again, what we are looking at is how do we add electronics capability, sensors, and so you now having smart structures. The challenge there is when you talk to a structural engineer and I want to add electronics to the structure, to them I'm adding a defect. So how do we get around those type of things, and how do you optimize? You know, in the certification and mechanical test world, there's tests for mechanical things, there's tests for electronic things. How do you merge those capabilities and the ways you monitor? Okay. So where we're looking at is, again, looking at electronics. So if you look at the industries out there, additive manufacturing is relatively small compared to everything else. Print electronics is the ability to print electronics using digital printing technologies, whether it's inkjet printing, direct printing, those kinds of things. And then where we're looking at is how do you move into the printed circuit board world and consumer electronics. So when you talk about printed circuit boards, what we're talking about moving into is printed circuit structures. So it's a different way. So form factor isn't flat anymore. It's basically this can be the form factor. And how do you integrate? There's a lot of reasons why you want to add electronics, sensors, to tell you whether something's about to fail. You can look at degradation of either built bridges, or you look at, you know, whether your tire in your car's going flat, losing air. There's a lot of reasons why you integrate sensors. The automobile industry is very hot and heavy on integrated sensors. Rolls-Royce is moving into 3D world. They're printing ceramic engines. It's not moved into production yet, but one of the reasons is you can get sensors directly closer to where you want to measure as opposed to assembling these things. The other thing is speed. How do we move to speed? You know, in our world is we add more print heads. With Nscript, our affiliate company, is we add more print heads. And basically we're printing cartridges of goo, if you will. So I'm doing ceramics, I'm doing plastics, I'm doing silvers, and how do I integrate those things? Okay, and then the other one is heterogeneity. In other words, being able to integrate. The cool thing about being able to integrate is you can, if you think of a mechanical problem where you've got material A and bonded to material B, if the coefficient of expansion is different, you've got a failure at that bond line. If I can mix the materials where I go from 100% material A to 90% material A, 10% material B, all the way up to 100%, now I have a functionally gradient structure, so I've now mitigated some of those coefficient of expansion issues. And if you think in the RF world, where you have impedance mismatches between an amplifier and an antenna, I can do the same thing by doing matching, and that's really the area that we're focused on is in the RF, because that's the hardest part of the electronics market to really address. Some of the things that are being done, this University of Texas El Paso, we have a relationship with them. They have probably one of the largest additive manufacturing capability at a university, wide-ranging capability. My partner, Ken Church, he's a co-director of this facility. These are examples of printed electronic things that we've done in the past. And in the breakout session number 2, I'll get in more detail of this. This is the RF stuff. This is where we're taking plastic ULTEM materials and 3D printing the substrates themselves, and then 3D printing the patterns that give you whatever RF functionality. My background is at Harris Corporation, so my background is in communication systems. This is for phased array. Our phase 2 Air Force program is to integrate some of this into a wing structure where we print the wing structure and do the communication systems within the structure. This is some examples, again, some people that we are currently working with. You know, the other things, there's a lot of pioneers out there. You know, we've got NAMI, which is the facility that was put together at Dayton, along with Penn State. They basically round 2, and I think we're, as a group, going after round 2 for a facility. So there's a lot of funding that needs to be happening and to take care of some of the manufacturing process issues as well as the material issues, particularly when you're integrating multiple materials. And so again, when you're talking about 16 smartphones per second, that's a lot of smartphones. If we think we can print probably 4 an hour, but that's a challenge. So that's the things that we have to go address. But the challenge is when we compete with China is when they optimize their production line. If you think about printing pages, they get really good at printing page 1. What we want to do in the 3D world is being able to do page 1, 2, and 3 in the same production line. They optimize into one product. We think we can do multiple materials because, again, you're spatially controlling materials and being able to do that. So opportunities, certainly DoD, that's where we live, but certainly mom and pop, this is going to be an interesting opportunity for them because they can address regional and local markets. When we talk about China, they make lots of things that come to the store and you only have a selection of a few. If you want to personalize your product, which is where everything's going, you can do that locally and be able to address local markets. And that's really the power of this. Certainly consumer and then apps. We all have apps for our cell phone. Ultimately, you're going to download 3D apps and be able to buy an app and then 3D print a product as opposed to going to the store. So if you have a knob break on your appliance, you download the app, you print it, because ultimately you have a 3D printer at home. And so those are the opportunities that are ahead. Ultimately, we think your distributors are going to print you a car, probably 20 years from now. But again, the manufacturer of car industry is looking into how to fabricate. So, and that's it. Thank you.
How you doing? My name is Ray Walker. I'm with the small company Keystone Synergistic Enterprises. And I'm going to talk about two quick topics today, both advanced technologies that are interesting. And, oops, let me see what we got here. Uh-oh.
I'm not sure they're there, Ray, I'm sorry.
Uh-oh. All right, while we're loading up. We're a small company located down in Port St. Lucie, just south of here. We're primarily in the metals world. We're out of the aerospace gas turbine engine community. So our background is metals processing, metals forming. And so we've been involved very heavily with two technologies. One is friction stir welding, which I'll talk briefly about, and the other is the additive manufacturing world. And so what I'd like to offer is that both these technologies have got a lot to do with energy efficiency and high productivity. There are aspects of them are low consumption of energy during the manufacturing process, but it saves a tremendous amount of material in the process. So we'll kind of look at those and some opportunities. The other thing I want to look at is a little company like ours doing business with somebody like big NASA. We had some discussions on that earlier, and I just want to show a few examples of what we're doing there as well. Looks like we're just about there. Okay, so I'm going to talk about friction stir welding and additive manufacturing. Let's see if we can, all right, that'll work. So we're located down in Port St. Lucie. Again, we're out of the engine OEM background. We've got essentially six people, so we are a small company. Again, I'm highlighting the friction stir and additive manufacturing. I'll give you a quick tutorial on what those are. We're very heavily into advanced alloy systems, the titanium nickel alloys, aluminum, iron-based alloys. And we're also involved some with the 3D printing of engineering prototypes, primarily the plastics. We're basically aligned with several other companies. We don't do a lot of production ourselves. We work with other companies. For instance, the red stars are other companies involved with the additive manufacturing side. So we have Atlantic Precision, which does the powder bed work. I'll talk about that a little bit. Huffman Technologies in the Carolinas, which does powder and wire feed laser, and electron beam deposition with Acceleron up in the Connecticut area. And with our friction stir welding that I'll talk about, we've been working with NASA Marshall in Huntsville, Alabama, as well as the Machute Assembly Facility in New Orleans. So we'll kind of look at some of these. All right, friction stir welding, what is it? Most welding of metal happens with a torch or an arc. I melt the metal to make a joint between two pieces of metal. What friction stir welding does is it heats the metal up to the point where it's soft and can be stirred together without any actual melting. So the kind of the diagram at the upper left, you have a rotating tool. You can see the tool in the middle, which has a protruding pin and a shoulder. And basically, I'm going to plunge that pin into the material so that it's buried up to the point of the shoulder. So I've got a rotating tool. I plunge it into the joint. I get frictional heating. And then as I'm rotating, I'm stirring. And the metal is in a plastic state now, and it's joining. So the benefits of this are it's really very low distortion, higher strength, and lower cost. If you look at a typical fusion weld joint where I melt the metal, on thicker materials I may have to make 5, 6, 7 passes of welding to make a joint, whereas with friction stir welding it's one pass. So you get a lot of productivity improvement just from that aspect of it alone. One project I just wanted to highlight that we were involved with was a Office of Navy Research funded project for what's called a T-craft. This was about a 220-foot long catamaran with deployable skirts that transforms itself into an air cushion vehicle. So again, for bringing assets ashore from offshore. And this was being slated to be built out of either aluminum or steel, but they wanted to look at a titanium component of that. So what we did is we took a cross-section of that hull, full-scale section of the hull, and basically showed how to manufacture that using titanium. So our friction stir welding we did, which is the plates, the deck plates as you're seeing kind of in the middle picture up there. Those kind of light joints there are all the friction stir welded joints that were made in the titanium material. It was then hand welded with all the frames and stiffeners and then incorporated into the actual structure that you're seeing in the lower right hand corner there. But the unique thing about this project is Again, a small company like us who does the friction stir welding, we don't own friction stir welders. But guess what? NASA owns the largest friction stir welding equipment in the world, and so it was fairly easy activity for us to go to the National Center for Advanced Manufacturing, which is part of the Machute Assembly Facility, as well as working with Huntsville. But the center picture there is a piece of friction stir welding equipment that's 120 feet long. It's got multiple heads, it has 3 rotary tables, and it's designed to make rocket cryogenic tank components, so dome structure and whatnot. But we were able to come in and borrow one corner of that to do this shipbuilding project. And so on the far side, you're seeing kind of a friction stir weld joint along the brighter stripe that you're seeing between the 2 fixtures there is actually the joint. And here we see one of the gentlemen actually at the head of the friction stir welding machine where the plate welding is being done. The other work we're doing in friction stir welding is for airframe structure in aluminum. This is a section of the F-35 aircraft looking at complex joints. How do we get rid of fasteners? Because everything is bolted together and fasteners add a lot of weight. So this was a project we had with the Air Force, again using friction stir welding equipment to demonstrate things like these frame components and things like that. But this is rapidly translatable to the automotive industry, to consumer products, marine industry especially. One of the emerging things that's really exciting is for liquefied natural gas tank transport in aluminum tanks. These are great candidates for friction stir weld technology. So the marine industry has picked up on friction stir welding quite readily, especially Europe. They're way ahead of us, but certainly can be applied. So the takeaway here is we as a small company had access to the largest friction stir welding equipment in the world. How do we do that? We leverage those assets primarily by putting Space Act agreements in place with NASA. Now the ones we designed, we had an umbrella Space Act agreement that allowed us to have one Space Act agreement, and we would come in with annexes for each separate project. So we basically negotiated one Space Act agreement, and then each new annex to it had its own statement of work, its own pricing, but we could rapidly bring in projects such as this. So these addendums under this umbrella Space Act agreement really was a good vehicle for us to come in, use this equipment. In some cases, we actually had our own operator using the NASA equipment. Other cases, or most cases, we have NASA operators using equipment. This is good for technology or light production work. And so it's just a good partnership and a way of doing business for assets that we're not going to go out and buy. Okay, let's switch gears real quick and talk about additive manufacturing. There's 2 basic forms. We're primarily out of the metals world. There's 2 approaches for it. One is powder bed fusion techniques. The other is directed energy. Powder bed fusion is a bed of powder, and I'm tracing through an electron beam or a laser a pattern on it. And I roll in a new layer of powder, and I repeat a pattern. I roll in a new layer of powder. So you see this, again, layer by layer buildup. With directed energy, it's more like an arc or a laser beam and adding powder or wire to a melt puddle. So they're very different in scale. This is very small. We can get up to parts that are hundreds and hundreds of pounds with directed energy. So I'm just going to kind of feature both of those real quick. This is electron beam wire feed. So the part you're seeing at the upper left was about 30 inches in diameter, about 300 pounds. It's made entirely out of weld wire, layer by layer by layer. The alternative to this was a 1,600-pound forging. This was a 300-pound prototype part. So for rapid prototypes of large, this has to be for gas turbine engine parts, some examples of larger parts we're making. So the 2 on the left are both for Rolls-Royce Corporation. The one in the middle is kind of a General Electric application. Again, mostly prototypes, nothing's in production yet. Electron beam equipment, you can see on the right, is primarily done in a vacuum. A beam creates a melt puddle by which we insert weld wire into that to build the 3-dimensional geometry. Other examples of small parts made with the electron beam process. A few of these I have on the table out there. You can come look at those. Again, making intricate shapes, but in general, this is different than 3D printing in that most of this requires machining all over. It doesn't create surface finishes that are good enough in general for final product. So in most cases, you'd see machining all over. In our Port St. Lucie facility, we have a robotic MIG system that we've adapted for additive manufacturing. In the lower left, we're making actually it's a composite layup tool for Boeing. That's about 550 pounds. It's about 6 foot by 4 foot. So that's probably one of the largest additive manufacturing structures made, but this isn't intended to fly in an aircraft. This is a piece of tooling. It's easy to qualify. So we went with the robotic MIG because it's a very low-cost platform. We can make non-critical hardware. We're working with the Army as well on some components on the right-hand side over there. Again, non-critical components that can rapidly be made. The idea is that a robot could be put into a shipping container with a gen set and a computer space, taken to the field and be able to basically create geometry very rapidly for vehicle and ground support. Okay. Powder bed technology creates net shape parts. Again, I got a few parts out there. Again, this is very intricate. This is a slow process. It's making very high quality, very intricate components. This happens to be our company right next door to us that we're partnered with, Atlantic Precision. And again, a lot of these shapes you're seeing are net shape, and they're intended to be high precision components that usually require a media finish to generate the surface. So again, we've got a few of those parts out there. It takes a long time. The big part in the middle took about 40 hours to print. So it is a slow process, but a lot of people are anxiously advancing that. We've heard about the plastics. Again, we've got a few examples out there. We've got the Stratasys machine, mostly for engineering prototypes. So we're primarily metals guys, but we use these a lot for mock-ups. Okay, kind of in conclusion, friction stir welding is rapidly expanding into marine. These are technologies that should be important to the Florida area and this region. I think can support those. Aluminum cryogenic tanks for liquefied natural gas. This is going to be a huge industry that's about to spawn. Many light metal products in the consumer industries, you're seeing that. Additive manufacturing is expanding just about into every industry sector. Hang on, it's going to take off. When the design community understands additive manufacturing and the materials that it produces, and we're starting to design for additive manufacturing, that's when it's going to take off. Today in metals, mostly we're doing additive manufacturing to substitute for a forging or a casting. But when the design community designs for additive manufacturing, that's really the key to it, and that's where our university components come into as well, and preparing that future design environment for the additive manufacturing. And I think that's it. Any questions? Thank you.
Hello, my name is Johnny Bohmer. I'm here with Performance Power Materials. My team is with us as well. And we're from West Palm Beach, Florida. We're a small company, and we're mainly here to talk about the Pandalloy aluminum that was developed by Pratt & Whitney. And we hold a license agreement for that. And we're exploring a lot of different areas in the Pandalloy market. Some of the stuff I'll talk about here. We have the car out front as well. I'll speak on that in just a minute. So we have three different verticals on Pandalloy that we're going to discuss, and these are just some of the examples of an extruded Pandalloy that went through the multiple stage process through powder, canning, degassing, and then through the final extrusion process. So this is the Gen 2 Pandalloy. Pratt & Whitney started this program with the Air Force about 11 years ago, and they decided to work on the Gen 1 project, which is basically a 5000 series Pandalloy. And it's graduated to a Gen 2 process, which we have gotten up over 900 degrees and still holding some real high tensile strengths and still have elongation, ductility, and it's turning out to be a really unique metal. And we feel it's going to be an aluminum alloy that can change the world in a lot of areas where failure is not an option. And hopefully the price will come down as we continue to make more product. And we also have some cast versions of Pandalloy, which we are currently developing a 355 and a 356, possibly a 319 series as well. And these are going to be geared initially for the automotive market, but we're seeing, we're having a lot of calls and a lot of interest in these different alloys. And then the last vertical we're working on, what my colleague was just speaking about, is additive manufacturing. We're currently involved in a project with Pratt & Whitney in West Palm Beach for a complete program of seeing how well Pandalloy works at its powder phase in additive manufacturing. And what we're hoping is that the L1-2 phasing process, because of how quick the laser hits the powder, that it doesn't lose its integrity, which is the drawback to a lot of aluminums, is that when they get hot, especially in some of these applications, they don't hold the temperature, causes them to lose their structural integrity. So let's see what the next. I got a little ahead of myself there. I'll try to go fast so that everybody's hungry. This is, Pratt Whitney did spend about 11 years and millions of dollars developing this alloy, so we're very gracious that they've allowed us to have a license agreement for it. And we're targeting several markets, but right now we're kind of concentrating on about 5 of the target markets we think that can generate some traction as far as funding goes. These are some of the materials that we have the patents on. We go 1 through, as you see, 7,000 series, and we have a lot of interest from multiple different entities, including the Department of Defense, for a lot of different things in this metal, whether if it's a wrought material or if it goes through the full extrusion material process. So, and then we're currently also working on a Gen 3 product, which is not listed up here, with the United States Air Force Pratt Whitney. These are the 50 cast patents that we have with Pratt Whitney, and Dr. Awad Pandey, who was going to try and come up today, wasn't able to come up, but he is going to, he actually did about 125 variations of each one of those patents. So Pratt Whitney spent quite a bit of time protecting their patents in their development stage of this, and it's a scandium-based alloy. All these use rare earth elements, scandium, palladium, hafnium. They use a bunch of different alloys, a bunch of different rare earth elements to create the alloy. The expert in laser sintering sitting over here, I know a little bit about it, but you know, I agree with him. I think it's the wave of the future. Instead of subtractive manufacturing, which we're all familiar with a Bridgeport and all the stuff we've grown up with, you now have the ability to make parts that are not near net shape, they're a done shape. And we're currently developing some different products, and we're working on some additive manufacturing, such as a piston for a car, where you can design the interior, as he was saying earlier. You design the parts to work when they're done. You have a honeycomb structure inside of a piston. This would allow the piston to be lighter. It lowers rotating mass on the engine. The engine's going to get better fuel economy. It's going to last longer. You can change the way the piston's made, because you could never do this with subtractive manufacturing or casting. You can't get the material away. So these are things we see in the future. This is why we're excited, because one of the verticals we're working with Pratt Whitney is if we can get the Pandalloy powder to work well in the additive manufacturing process, which it's still in experimental stages, we see a huge leap, because we're currently able to outperform titanium in about 65% of the applications that we've identified in the aerospace industry. And due to the fact that we can increase wall thickness slightly and outperform titanium because we're lighter. The car outside, if you wonder why it's there, the turbine wheels in the back of the compressor housings on the turbochargers, we took the original billet turbo wheels, and we decided to go ahead and design a